Okay, so some review. Last time we did a lot of review. It ended up being 45 minutes worth of review. But we did get a little bit new in. So let's start, I guess, with our review of our review. So this will be important for today. When the derivative is greater than 0 means f is increasing. And I guess we didn't technically define what it means for f to be increasing, but I think intuitively we all know what it means. It means that as we plug in larger x values, the function returns larger y values. It's very intuitive. In the picture, it looks like it's going uphill as you look from left to right. When the derivative is negative, when it's less than 0, that corresponds to where the function is decreasing. And of course, the function can be increasing in one area and decreasing in another area. And we can actually figure out what intervals it's increasing on and what intervals it's decreasing on. Another thing we talked about was the first derivative test. Now, the first derivative test, the key here is that it uses the first derivative. And so when you're using the first derivative test, of course, you look at the first derivative. And the idea is you find your critical points. And you find critical points by looking at the derivative. Suppose our critical point here is a. And you look on the left and on the right of that critical point. And you say, what's happening with the derivative? And the reason we're doing this is because what's happening with the derivative tells us something about how our function is behaving. And we want to know how our function is behaving around a. So for instance, if our derivative is positive on the right, left, and negative on the right, so that it's increasing before a, decreasing after a, then our curve looks something like this. Now, this is a really lousy picture of what's happening with the function. And today, we're going to get much better at drawing these pictures. But this is just to give you a rough idea. It's going up, going down. So it's at a max. If it's negative on the left and then positive on the right, again, draw a lousy picture. It's going down and going up. So that our point is at a min. If it's negative both left and right, we go down and we go down. Or it can be positive both left and right, and then we go up, and then we go up. And all of these things are possible. For instance, here, this is an x cubed. This is like x squared, and so forth and so on. Another thing we talked about last time was Rolle's theorem and the mean value theorem. And the mean value theorem says that if you have a continuous function on an interval from a to b, and it's differentiable, which means that we can always take a derivative on any point in between a and b. So this idea of differentiability says something about the function is smooth. It doesn't have anything like the absolute value of x function, where the absolute value of x has like this V shape. Where it's something like, it almost looks like you took a straight line and you broke it, So saying differentiable says it's a nice, smooth curve. And the result is, if you have these two conditions, then there is at least one, and possibly many points, C, in between a and b. So there's some C with C lying strictly between a and b. So that if I look at the derivative at C, it's equal to the value f of b minus f of a over b minus a. Now this f of b minus f of a over b minus a, this is the average rate of change. This is the instantaneous rate of change. And so we drew a picture saying, well, look, this is like a secant line through the points AFA and BFB. And what it's saying is there's some tangent line parallel to that secant line. Or if you like, at some point, our instantaneous rate of change is exactly equal to our average rate of change. And there's a nice corollary. In fact, there's many corollaries, or corollary, depending upon how you pronounce it. It says if your derivative is 0, and I'm not talking about 0 at a point, but 0 everywhere for all values of x, then the function that you started with was a constant function. That's the only way you can get a derivative that's 0. Assuming, of course, you have these nice conditions. That'll be important in the next chapter, building up to chapter 5 and chapter 6. Okay, so that was the review, which took most of our class. So today, we're going to finish up what we started last time, which is concavity. So the concavity is saying something about how the shape of the curve looks. There's two basic ideas. There's concave up and concave down. Let's go with concave up. Well, another word to think of this with concavity is this word bending. So when we're saying concave up, the curve is trying to bend upwards from a point. This is just intuitive. This is not very rigorous mathematically. So what's more rigorous is, well, the slopes are increasing, or another way to think about it is that the derivative is increasing. So we're saying if we're concave up, if the derivative is increasing. Here are some examples of what I mean by being concave up. The curve is trying to go up. So imagine that this were a flat line. I'm trying to bend it upwards. And you can actually see what happens if you go along any of these curves, here I start with a very large negative slope, and it gets to a smaller negative slope till I hit 0. And then I start getting positive slope. Yeah, so a little positive, but more positive, more positive, more positive. So I'm going from a large negative to a large positive as I go from left to right. Here I'm going from a large negative to a small negative. Here I'm going from a small positive to up to a large positive. So these are all examples where the slopes are increasing. Well, if the derivative is increasing, if we come back over to here, remember, when is a function increasing? Well, a function is increasing when its derivative is positive. So when would the derivative be increasing? Well, it would be increasing when the derivative of the derivative would be positive, or in other words, the second derivative is greater than 0. So concave up corresponds to where the second derivative is greater than 0. Now, concave down. Similar ideas. Concave down, the idea is that now we're bending down. Instead of having our slopes increasing, our slopes are decreasing, or the derivative is decreasing. And again, you can go to any one of these three pictures here. Here I start out with a slightly small negative curve, and as I come down, it becomes more and more negative. So the slope was decreasing. Here I start off with a very large negative, but as very large positive, but as I come up, my slope is becoming more shallow, so it's becoming a small positive. Here are positive, small positive, 0, negative, big negative, so forth and so on. So these are examples where the slope is decreasing. And of course, the function being decreasing, if we go back over there, function is decreasing when its derivative is negative. Well, if the derivative is decreasing, then the derivative of the derivative, or the second derivative, is negative. All right, so this is what we talked about at the very end of the last class. Okay. So let's see, where does that bring us up to in my notes? That brings us up to here. Well, we can be concave up and we can be concave down. There are some points that might be interesting. When do we change from being concave up to concave down? These are called inflection points. This is where we change our concavity. So we either go from concave up to concave down, or we go from concave down to concave up. That's the definition of an inflection point. So in other words, on one side it's positive, on the other side it's negative, or vice versa. So how do we find inflection points? Well, we look at it and we say, well, look, concavity is totally determined by the second derivative. So really, I just need to look at where the second derivative, what's happening with that. So it's very similar to the inflection points are essentially, you can think of it as the critical points for the second derivative. So where can they occur? Well, they occur where either the second derivative is 0 or the second derivative is undefined. That's the places where we can change concavity. Anywhere else, then we're either concave up or concave down, and we don't worry about it. So for instance, we can make up a function. Of course, if we make one up, we'll get into trouble, so let me try not to make one up too badly. Unless this is any good. Okay, so suppose I say, here's my function. F of x is 3x to the fifth minus 5x to the fourth plus 1. And I ask, where are the inflection points? So what's our first step? Yeah, first step is, really want to get to the second derivative, so we'll stop in the meantime and say hello to the first derivative. Hello, first derivative. How are you? Oh, I'm doing good. How's life? That's okay. Okay, so there's the first derivative. Derivative of 3x to the fifth, of course, the 5 comes down. 15x to the fourth. Derivative of 5x to the fourth, the 4 comes down. 20x cubed. All right. So normally we'd ask questions about the first derivative. We'd say, where are the critical points? Where is it increasing? Where is it decreasing? Does it have max, min, and so forth and so on? And we can use the first derivative for that. Right now, I'm just worried about inflection points. So I'm just going to totally skip by the first derivative and keep going to the second derivative. So in our case, the 4 comes down now, so that's 60 x cubed. And now the 3 comes down, so that's 60 x squared. All right. So we're looking for inflection points. Is the second derivative, is it ever undefined? No, this is nice. Polynomials. We like polynomials. Okay, so we set this equal to 0. Now notice we can do some things. We can factor things out. So we have 60x squared, because they both have 60 and they both have x squared, times x minus 1 equals 0. All right, so looking at our graph here, so where are the places where second derivative is 0? Well, either we get it from here, which is x equals 0, or you get it from here, which is x equals 1. So if I'm going to have an inflection point, I don't know if I do yet or not, it's going to happen at 0 or 1. Okay, so I can do the same thing as I did before, where I draw a line, I mark 0, I mark 1, and I just basically say what's happening to the left and right of 0, what's happening to the left and right of 1. And the same basic ideas hold. In other words, if I really just need to say, plug in one value less than 0. Plug in a value between 0 and 1. Plug in a value bigger than 1. And see what's happening in each one of those areas. So for instance, if I plug in a number less than 0, anyone have a favorite number less than 0? Negative 1. Okay, that's a nice number. I can plug it either into here or into here. It doesn't really matter. So for instance, 60 times negative 1 cubed would be negative 60. Minus 60 times negative 1 squared, which is another negative 60. So the second derivative at negative 1 is negative 120. But again, I don't care about the 120. You really just need to make sure whether it's positive or negative. And in this case, it's negative, which tells me that before 0, what's happening? Well, before 0, I'm concave down. I have this kind of shape going on. One of these things is happening. I don't know exactly which one, but one of these basic kinds of things is happening. All right, what's the number between 0 and 1? Yeah, a half. Now, again, I can plug into either one of these. These are both the way to write the derivative. Let's plug it into here. Again, I don't care about value. I only care about sign. So 60 is positive. A half squared is positive. A half minus 1 is negative. So if I multiply it all together, I see that the second derivative of a half is negative. So again, I'm concave down before 0. And I'm also concave down after 0. What does that tell me about 0? Is it an inflection point? No, because I'm not changing concavity. So the inflection points are where we go from concave up or concave down. I should have drawn a picture here. So what does an inflection point look like? Well, it could be your first concave down, and then you have a point of inflection, and you're concave up. You might look something like that. Or you could, vice versa. You could be concave up. You could go to concave down. Or you don't even have to, there's all sorts of ways to do it. Concave up, concave down. So these are places where our concavity changes. So those are examples of inflection points. Okay, finally, plug in a number bigger than 1. Anyone have a favorite? 2. 2 is a good choice. 2 cubed is 8, 480. 2 squared is 4. That's 240. 480 minus 240 is 240. So f double prime of 2 is 240. But I don't care about the value 240. I just care the fact that it's positive. So this is concave up. Okay, so now what do we say about 1? It is an inflection point. So this curve only has a single inflection point, and it occurs at x equals 1. Now, let's think about 0 for a second. Now, if I look at this curve here, 0, I saw that it's concave down below 0 and concave down after 0. But coming back to the first derivative, which we said we were just going to pass by for a second and not really pay much attention to it, what do you notice when I plug 0 in? It's 0. So 0 is a critical point. All right. Well, let's pause for a second. Let's think about the following question. Given just what I've written down on the board, can we figure out whether 0 is a min or a max? Now, we already have a test called the first derivative test. But I'm not going to apply the first derivative test because I haven't written anything down about what's happening with the first derivative. And I haven't found what the other critical points are. So I don't even know how to test for the first derivative test yet. So let's think about it. Let's try to use the information that we have here. We know that 0 is a critical point, and that if I look around it, the curve is concave down. Well, what does it mean to be concave down? It means that the curve is trying to bend downwards. So whatever happens at 0, well, what happens to the right? It has to be bending down because it's concave down. What happens to the left? Again, it has to be bending down. It has to be concave down. So by looking at the concavity at 0, or in this case I should say the concavity around 0, I can tell that what's happening is that the curve is bending downwards. So that says my picture around 0 has to look something like this. So what can we say about 0? It's a max. Yeah, so we can use information about the second derivative to also give us information about whether a point is a min or a max. Well, that leads us to, lo and behold, the second derivative test. Now, technically, we actually didn't use the second derivative test, but what we did use is related. The idea is, let's use concavity to tell us something about our critical point. Now, the second derivative test is a great test. It's not as universal as the first derivative test. So the first derivative test, for instance, works for all your kinds of critical points. And when I say all kinds, there's really only two kinds, where the derivative is 0 and where the derivative is undefined. Second derivative test is not that great. First off, you have to have the derivative at a has to be 0. And the derivative at a, the derivative at a has to be 0. So it can't handle the case when the derivative is a non-exist case. And the second derivative of a has to exist. Because you have to look at the second derivative at a. And what you're using when you're looking at the second derivative of a, you're saying something about how is the curve bending around a. Okay, so if you have this, so you have a critical point, that's what this one says, and you can look at the second derivative, that's what this one says, then you have the following. If the second derivative is negative. Now, second derivative being negative means that we are concave down. That's this picture over here. It means we're bending down. So, for instance, this point here is a place where the second derivative is negative, and I have a slope of 0. So, in this case, what can I say about my point? Is a at a max or at a min? Yeah. Then I'll just say the point a, f of a. So either if you want the x value, it's a. If you want the y value, it's f of a, is a max. If the second derivative is positive, well, we're going to be able to make a similar statement. Then a f of a is something. Second derivative means we're bending up, we're concave up. So here is an example where I have a point where the first derivative is 0, then I'm bending up on both sides. So what's happening at this point? What is it? It's a minimum. It's at the bottom. Yeah, it's a min. Now, I talked about whether it's negative. I talked about when it's positive. What happens if the second derivative is equal to 0? Okay. Then we don't know. I guess I shouldn't put question mark, question mark. How about we put, then try harder? You're going to have to use something else. Usually in this case, you go back to the first derivative test. In our example over here, we actually ran into a case when the second derivative was 0. But we looked at the left and right and saw that it was concave down. And so essentially what's happening is that the second derivative really should be negative in some sense around at 0. That helped us figure out its max. Now, you might remember some pictures I drew a while back. So these pictures are associated with the second derivative test. So remember, if your second derivative is positive, your curve looks something like this. And of course, if you're at the bottom, you're at, sorry, I started with a negative. Okay, if your second derivative is negative, your curve looks something like this, and you're at a max. If your second derivative is positive, Your curve looks something like this. You're at a min. And this is, I don't know if I drew this face, but if your second derivative is 0, you don't know what's going on. So this is how I always remember the second derivative tests. So second derivative, so minus, minus. There's two of them. Your curve is looking something like this. Second derivative is positive, two plus signs. So curve looks something like that. And if your second derivative is 0, you can't really say much about what's going on. It could be an inflection point. It might not be. It could be at a max. It could be at a min. And it could be at neither. I mean, there are examples. It's not very hard to find examples. If you look at f of x, say, as x to the fourth, well, what does x to the fourth look like? It looks suspiciously a lot like x squared. You'd have a hard time, just looking at the basic shape and distinguishing x to the fourth from x squared. And so, obviously, just looking at the picture, we know that at 0, it's a min. But you can go check. F prime of x is 4x cubed. And f double prime of x is 12x squared. So you know 0 is a critical point, because at 0 you get 0. And when you plug 0 into the second derivative, you get 0 out. So here's an example where you have a minimum, even though the second derivative is 0. So you don't have to have an inflection point. All right. So that is the second derivative test. So now we have two tests for testing for max or min. All right. What else can we say about our second derivative test? Okay, let's skip ahead and go on to next chapter. Yay! I should say next section. Yay! So the next section is very outdated in some respects. This is something, a really important skill about up to maybe 10 years ago. Then after about 10 years ago, it no longer became important. But we still teach it. Because it's good because it helps build intuition. And this is graph drawing. So in other words, I have a function, and I want you to draw me a picture. Now, it's kind of outdated nowadays because we have all these wonderful tools, these calculators and computers that do it all for us. So nowadays, very few people actually master this. But it's good to sort of build up the basic tools of how you would do it, because it helps you understand functions. Now, the key for us is essentially we're just going to play connect the dots. Because we're not going to get the exact picture. Now, how do you get the exact picture? Well, the way you get the exact picture, if you have a function, is you start by making a list. So you have x, and you have f of x. And you might have at 0, you get 1. So, okay, so that means that you come over here, and at x equals 0, y equals 1, you put a dot. You might say, well, at 0.1, I'm at 1.2. Okay, so you come up to 0.1, you put 1.2. And then so forth and so on. Well, 0.3, you're up to 1.1. Now, what do you notice about this process? Well, one thing I notice is it's really boring. Because this is actually how you draw functions. This is technically how functions are drawn. You go through and you put a single point in. You put it in x, you find f of x, you put a point down. You put in another x, you put another point down. Another x, you put another point down, so forth and so on. You just keep going until you basically run out of energy. Now, the problem with this is, how many points do I have to draw? A lot. In fact, technically, I have to draw infinitely many points, because there's infinitely many numbers. So if I were to understand my function, I'd have to do this infinitely many times, which takes a while. So we say, oh, that's no good. So what we're going to do instead is we're going to say, well, look, I'm just going to find the interesting points. Now, of course, the question is, what's interesting? But we'll talk about that. We're going to find the interesting points. And then we're going to play connect the dots. So the graph pictures that we're going to draw are not exactly right, but they have all the right behavior. And so they give us a good intuition about what's going on. So really, this section comes down to two steps: finding the interesting points and playing connect the dots. Now, let's talk a little bit about connect the dots. The way we're going to connect the dots is we're going to look at the derivative and the second derivative between 2 points, and we're going to say, how is that behaving? In other words, are they positive or negative? And then depending upon what's happening with the derivative and second derivative, I'm going to have a different shape. So there's really 4 possibilities. So let's draw these 4 possibilities here. So one possibility is that the first derivative is positive, and the second derivative is positive. So we're increasing, and we're concave up between the 2 points. Well, that says our curve is doing something like this. We're increasing, and our concavity is up. Now, another possibility is that our derivative could be positive, and our second derivative could be negative. So that we're increasing, but we're concave down. So how do we do that? Well, that says we look something like this. So I'm still going up, but now I'm trying to bend down if I imagine this. And of course, I could do the derivative is negative, so we're decreasing. And the second derivative is positive. So if the derivative is negative, second derivative is positive, that says my curve looks something like this. And not many things left. The first derivative is negative, and the second derivative is negative. That says my curve is doing something like this. Okay, so what are we going to do? We're going to find our interesting points. We're going to play connect the dots. And then we use these basic facts here about how the curve should look, depending upon the signs of the derivative and second derivative, to help us have a realistic picture. Now before, I was drawing pictures before, but these are totally unrealistic. I mean, no function, well, some functions do, but most functions don't look like boom, boom. Most functions are kind of curvy. They're bendy. So it's good to have this intuition. Once you have this, then we're in pretty good shape. Okay. So what are interesting points? Well, these need to be points which are not too hard to find, or at least not too hard to get a good grasp on. So some interesting points are, say, x-intercepts, where it crosses the x-axis, or y-intercepts. Now, y-intercepts is really easy. Notice that here I put the s on, but here I don't. Just a t. So notice the subtle difference between the s and the t. Because there's only one y-intercept. And how do you find your y-intercept? Now, your y-intercept is where you hit the y-axis. When are you at the y-axis? When x equals 0. So you just plug in x equals 0. So you plug it into your function and see what number comes out. How do you find x-intercept? Well, you put y equals 0, and then you have to solve for x. Now, you might get no values of x. You might get many, and it might be hard to find. So x-intercepts can be hard to find. So we'll put some effort towards finding it, but we won't feel bad if we don't get them all. Okay, so those are some interesting points. Well, also some interesting points are critical points. So this is where derivative is 0, our derivative is undefined. Now, one of the reasons that these are interesting is because these correspond to max and mins. And usually maximums and mins. That's something that we're interested in finding. We're interested in finding the largest that a value of a function can be and the smallest that the value of a function can be. And we're going to have a whole section where all we do is try to say, what's the largest? What's the smallest? And it's good. It's like if you're in business, you want to say, well, what do I do to make the most money? You're looking for a maximum. You're trying to maximize your profit. Or maybe you're trying to say, what can I do to get the most amount of sleep? You're looking for a maximum. Or what can you do to go to the fewest calculus lectures? That's a minimum. You're trying to find these things. You always are trying to find the optimum value. And we're going to talk about how you find maxes, mins, and optimize. And that's our next section. But today, okay, so critical points, intercepts. We also have inflection points, where the second derivative is 0, and perhaps second derivative does not exist. Usually when the second derivative does not exist, it corresponds to where the first derivative does not exist. Again, because once we have inflection points, we can sort of see how we're changing from one concavity to another concavity. Now, technically, these aren't points, but these are some interesting points, interesting parts of the curve. So I'm going to throw these in. These are asymptotes. Now, when we talk about asymptotes, there are two basic kinds of asymptotes. There's what we call the vertical asymptotes. And vertical asymptotes in our class basically come from one thing. It's when we have a number that's not 0 on top or a number that is 0 in the denominator. That's an example when we have a vertical asymptote. So like 1 over x, at x equals 0. Because I'd have 1 over 0. Of course, when we have 0 over 0, then it gets a little bit trickier. We have to play around with it and take limits and try to figure out what's going on. Usually the function is undefined. Now, another kind of asymptote is horizontal. And basically that's saying what's happening to my function as I go to the very large x value. So the limit as x goes to plus infinity and negative infinity of f of x. And technically, you really should have two kinds of horizontal asymptotes. You have a horizontal asymptote as you go to positive infinity. You have a horizontal asymptote as you go to negative infinity. Now, in some algebra classes, they still teach what are called slant asymptotes, and they're just a variation of horizontal asymptotes. So slant asymptote is when, as your function goes off to infinity, you don't approach a constant, which is what we care about here in horizontal asymptotes. It's basically saying limit as we approach infinity or negative infinity is some constant k. Slant asymptotes are where we approach a line as we go to off to infinity or negative infinity, and we're not going to worry about that in this class. All right. So let me, sorry. Just takes a while to clean the board, clean the board. Now, one thing that the book does is they have another terminology here for these interesting points. They have what are called transition points. And essentially, it's one of two things. Either, well, I'll just list them. The function goes from increasing to decreasing. Or vice versa. So in other words, one example of a transition point is when we go from having an increasing function to a decreasing function. So essentially this is where critical points. The derivative is 0, derivative does not exist. So the other thing is if the function goes from concave up to concave down, or vice versa. So again, this is basically just saying it's an inflection point. So if the book asks you, say, on a problem on homework, about what can you say about these transition points, or where are the transition points, or what kind of transition points are they? What they're really talking about is what's happening to the function. Either something happened to the derivative where it went from positive to negative, or something happened with the second derivative where it went from positive to negative, or it could have gone from negative to positive. Now, it's pretty easy to sort of pick points out. So here, if I want to find transition points, I see a transition point here, and I see one here, and here, here, here. Okay, so what's happening at this first transition point here? Let's call it A. What happens at A? Yeah, the derivative went from increasing, our derivative went from positive, to the derivative went to negative. So here, the transition was, on this part, if I look to the left of A, the derivative is positive, second derivative is negative. And to the right of A, the derivative is negative, and the second derivative is positive. Oh, sorry, negative. Second derivative is still negative, still concave down. So this is a transition point where it's the first derivative that does the transition. First derivative went from positive to negative. Okay, what happens at B, which is the next point across? The concavity changes. Because here, the curve is still decreasing on both left and right, so the derivative is still negative to the left and to the right. But now what happens is it goes from the concavity being down, which is second derivative being negative, to concavity being up, which is the second derivative being positive. So here it's the second derivative that made the transition. All right, how about at the next point, C? Yeah, it's the first derivative changing. First derivative is greater than 0, and second derivative is still greater than 0. And we can go through every single point here. So that's finding transition points. Now notice that once we have these transition points, if I erase the curve that I came from, suppose I erased this part of the curve. But suppose I knew that I'd already found these interesting points A, B, C, and let's call this last one D. And I'd been able to plot the value of the function at each one of these points. So I came through and I was able to figure out what height they were at. Then how could I estimate drawing the graph? Well, I just go through. This is just an idea of what we're going to be doing. We'll do some examples. And I just basically connect every single consecutive pair of points according to the rule. So first derivative positive, second derivative negative. And I say, okay, where's the first derivative positive, second derivative negative? Is this kind of shape here. And I should also say, I know that A is where I'm switching from having positive slope to negative slope. So it's really, I would even be able to say more. I would be able to say that it has slope 0. And certainly I know that C has slope 0 because I would be able to look at the first derivative. So my curve looks something like this one. So to the left, I have to be doing something like that. First and second derivative are both negative. That says that between here and here, I have to have my curve doing something like this shape. So I just put roughly that shape in, keeping in mind that I start with 0 slope. And so I come in, and I just go down. First derivative negative, second derivative positive. First derivative negative, second derivative positive says I'm doing this kind of shape. And so I come in, and I just remember that at the end, I have to be coming into 0 slope. First derivative positive, second derivative positive. So now I'm doing this kind of shape. So I'm coming in from slope 0, and I just keep going up. And lo and behold, you'll look, and I see I pretty much got the exact same curve as before. And that's the idea of this graph sketching, is you find the points, mark them on the graph, play connect the dots. Now, the way to really do this is just to do a lot of examples. So let's start with a very simple example. Let's do a sketch. Y equals x cubed minus 3x plus 2. So I want to get a really good drawing of this graph. We actually drew this graph way back when. But now we'll see how we were able to draw it fairly quickly. All right, so first off, let's talk about some various things. Where's the y-intercept? Yeah, it's at 2, because I basically plug x equals 0 in. 0, comma 2. How about x-intercepts? Can we find them? Well, that says we have to solve a cubic. And sometimes we can solve cubics and we can get lucky. Now, in this case, can we solve it and get lucky? We can. We can get lucky. Now, there's something called the rational root test, where you say, okay, if it's a polynomial with integer coefficients, you only have so many different possibilities it can be, and then you can go through it and test it. I don't expect you to know that. So unless it's obvious what the root is, don't worry about finding it. In this case, you can. They're at 1 and negative 2. And you can check. When you plug in 1, what happens? You get 1 minus 3 plus 2. And lo and behold, 0, woohoo. Negative 2. Negative 8 plus 6 plus 2 is 0. So 1 and negative 2 are roots. And it turns out these are the only 2 roots. Okay, so don't worry too much about the x-intercepts. These are not quite as important. Y-intercepts also not the most important. What are important? Are critical points and inflection points. So let's talk about that. Critical points, I look at the derivative, y prime. What's the derivative? Yeah, 3x squared minus 3. Now, this, of course, always exists. So I'm just going to look at when does the derivative equal 0. Well, so y prime equals 0. Well, that corresponds to when 3x squared minus 3 equals 0, which is the same as x squared equals 1, which is that x equals 1 and negative 1. So at plus and minus 1. Okay, so now I know where we have critical points. Let's classify these critical points. So let's draw a quick picture. I'm going to put negative 1, 1. Okay, I pick a value below negative 1. Let's say negative 2. And I plug it in. And I see that f prime is positive below negative 1. Between negative 1 and 1, I can plug in 0. I get negative 3 when I plug into the derivative. Let me use y since I haven't used f. Y prime. So y prime is negative. And then above 1, I can put 2. And again, I can see that y prime is positive. So I'm coming up. I hit whatever the value is at negative 1. I go down. I hit whatever the value is at 1. I go back up. So this is a really lousy sketch of the curve. But we're going to do something like this. Come up to whatever my value is at negative 1. Go down to wherever my value is at 1. And go back up. All right, we'll improve on this picture. Okay, but so we can know right away that negative 1 is at a max. 1 is at a min. Now let's talk about second derivative. 6x. Again, never undefined, but it does equal 0. Where does it equal 0? Yeah. So y double prime equals 0 at x equals 0. And again, is this an inflection point? Well, I can mark here the second derivative 0. What is the second derivative below 0? It's negative. So second derivative is negative. What's the second derivative after 0? It's positive. And so I change from being concave down to concave up at x equals 0. Now, I could have used the second derivative to classify negative 1 and 1. Let's just make sure it works. If I plug negative 1 into the second derivative, I get negative 6. So I get a negative for the second derivative. So that tells me that negative 1 is at a max, because a negative second derivative at a critical point means you're at a max. And I could have put 1 into the second derivative, and I would have gotten 6, which is positive. And so that tells me that 1 would be at a min. Okay, so the first and second derivative tests were consistent, which is good. They should be. All right, so now we found our interesting points. We found x-intercepts, critical points, inflection points. Asymptotes. Are there any vertical asymptotes? No. Yeah, essentially right now, just look for division by 0. So we have no problems with vertical asymptotes. What about horizontal? Well, what happens to this polynomial as x gets large? And the moral is that polynomials get big as x gets large. So there's no horizontal asymptote because I'm not approaching a number. I'm getting really large. So there's no horizontal asymptotes. All right, so now we can draw our points. So we have a point at 0, 2. And then I say, okay, there's an interesting point at 1. There's an interesting point at negative 1. I plug 1 into my function. I get 1 minus 3 plus 2, which is 0. So I have an interesting point here at 1. I also know that 1 is where I have a flat tangent line. So one thing I like to do is I just like to mark that on my graph. So I know that I'm going to have a flat tangent line at 1. What happens when I plug in negative 1? Well, I'll get minus 1 plus 3 plus 2. So when I plug in negative 1, I'm going to be up here at 4. And again, this is where the first derivative was 0, so I'm going to have a flat tangent line. So let me just put some notes here. So that's at a max. This is at a min. 2. This is an inflection point. So you usually don't have to write all this down, but I'm just writing this down to help us recall. So we found these interesting points. The critical points where the first derivative was 0, and this inflection point where the second derivative was 0. And now we just basically go through what we did before, and we say what's happening in each one of these pieces here. So what are my pieces? Well, I have below -1, between -1 and 0, between 0 and 1, and bigger than 1. And I look at what happens with the derivative and what's happening with the second derivative. So here, if I just look at my chart over there that I made, this says the derivative is positive, and the second derivative is negative. Here, from -1 to 0, looking at I'm looking at these two charts here. I saw that my derivative was now negative, but my second derivative still stayed the same. So this was a transition point for the first derivative. Between 0 to 1, my derivative stayed negative, but now my second derivative went to positive. And bigger than 1, I see that my derivative is now positive, but my second derivative didn't change. So I mark my points. I figure out which one of the 4 behaviors happens in each one of the intervals. So when I mark the points, essentially, I split it up into intervals according to where I have these critical points and these inflection points. And now what's left? We play connect the dots using this basic rubric here. So for instance, I start, the first derivative is positive, second derivative is negative. First derivative positive, second derivative being negative means that it looks something like this. So I'm going to come up, and then when I hit this max, I have to have 0 slope. So I'm coming up from somewhere. In fact, we know where I'm coming up from, because we found this point, which is not very important, but okay. Come up, and we hit. We come in slope 0 at the top. Now, first derivative is negative, which means I'm going down. Second derivative is negative. So I look and say, aha, first derivative negative, second derivative negative. So I'm going to go down to that point 0. So it looks something like that. And now I'm going to switch my concavity, but I'm still decreasing. So first derivative negative, second derivative positive, which is first derivative negative, second derivative positive. It's this one. So now I'm getting concave up. So hopefully if I get the picture right, you should see that concavity changed at 0, 2. And I came in, and I hit this line, and I should have a slope of 0. And now first derivative and second derivative are both positive, so I'm up here, and away I go. So there is a graph of y equals x cubed minus 3x plus 2. It takes a little bit longer than if you just plug it into a computer, but it doesn't give you the same satisfaction, you know? Plugging into a computer, you learn something. We're not done. I got a minute. Okay, we'll finish up next time. All right.